Okay, I'm just going to go through some of the definitions that you're going to need for the motion in 2 or 3 dimensions in the kinematics section. We need to have a good understanding of vectors, and we also need to have a good understanding of kinematics from year 12, so you might want to make sure that you've done the review in the start of chapter 18. So first of all, there's a couple of definitions that we need to go through, and the first one is the position vector. So the position vector is given the symbol r. And again, I'll just change pen. So it's an r that we're going to end up giving for the position vector. Now what the position vector just basically means is that it is in relation to the origin. So again, it could be written as a column vector of x, y. And again, remember it's coming from the origin. If we've just got an r, it's going back to the origin in the x direction and the y direction. It means that we can work out the magnitude of this position vector, just like in the previous bit. We end up saying that the magnitude is just basically Pythagoras square root of x squared plus y squared. And remember that if the magnitude of the position vector, this will end up given as the distance. Now so that's the position vector and the distance. If we now look at velocity, we know that from our speed, distance, time graphs that velocity is the change in the position over time. So how we would write that mathematically is the small change in the position over time. And this gives us the velocity. Now if I say that the position of the object is x in the I direction plus y in the j direction, then by finding out the velocity, you can see that this kind of involves differentiation. So if we differentiate this position vector, so this is the position vector, then we will end up getting it in terms of velocity, which means that dr by dt is equal to dx by dt in the I direction plus dy by dt in the j direction. This means that we could also write this as a column vector to say that the velocity is dx over dt dy over dt. And that would be the velocity. Now we also know that velocity, if we work out the scalar velocity, then we end up getting the speed. Therefore, if I work out the magnitude of the velocity, so the magnitude of the velocity, then I will end up getting the speed. So again, dx by dt all squared plus dy by dt all squared, and that will end up giving us the speed, which is in the velocity. Now from the velocity, if we look at the change in the velocity, so if we've got dv with respect to time, then we're going to end up getting the acceleration, because the change in velocity over a small change in the time will end up equaling the acceleration. This means that if we compare this to the original position, we had to differentiate to get the velocity, we differentiate again to get the acceleration. How this can be written is if I take it from the position vector, which we've got here, it would end up being that the acceleration dx, so that's double differentiated, in the I by dt in the j. and this would end up giving the acceleration in relation to the position. Now again, we could work out the magnitude of the acceleration. So the magnitude of the acceleration would end up again using Pythagoras. Over d squared t all squared plus d squared I over d squared t all squared. And that would get us the magnitude of the acceleration. Now this basically gives us a general rule that we can look at, where we've got, if we've got the position and we want to change to velocity, then we end up differentiating, and if we differentiate again, we get the acceleration. Now going this way, we're differentiating, and going the opposite way, we're going to have to integrate, and we'll talk a little bit more about that in the next one.